So a few of you probably know who I am. I've been the kernel graphics maintainer for quite a long time at this stage. And about 2 or 3 years ago, maybe longer, I came up with this idea of doing a proper virtio-gpu. And it's taken me this long to get anyone to let me do it. But they finally let me do it. So I started it about, say, 6 months ago, I think I started working on this. So I'm here today to sort of give an overview of where it's at and where it's going and what sort of work is involved in it. So yeah, as I said, it's one of the things I have to say as a disclaimer. It's a research project. That's my Red Hat's bit of the job out of the way. But yeah, basically this is not a product. This is not going into any products anytime soon. This is not part of our Spice project. It's not part of our Rev platform. None of that. It's a research project by me, for me. Nobody else uses it. But yeah, basically the idea was to build a proper virtual GPU that could do 3D acceleration. The thing that made it sort of possible was we had the gallium hardware model that we have in Mesa, which was a low-level enough interface that sort of basically tries to even out what hardware exposes into a sane interface that isn't something like OpenGL. So the idea was, well, we could use this model to represent a PowerVirt device. So that was one of the first things that sort of made it possible to do this. Funny enough, that code came mostly from VMware, or from an acquisition VMware made, so it was kind of useful. It's Linux focused so far. I've not looked at anything else in the guest. There are possibilities of using Windows in the guest, but I'm not going there. That's somebody else's problem. But yeah, today I'll just start off with a bit of a history of current virtualized graphics, look at the basic virtio-gpu, a bit of a quick hardware description of how the basic one works, a bit of information about the 3D side, some of the issues we've faced getting so far, and some of the QEMU problems and other side projects we've had to sort of deal with to get this going. So just a quick history of the area. There's been a few projects in this area already. Closed source ones, VMware have had their SVGA2 device for years. They had 3D support probably 5 years ago, maybe 4 or 5 years ago. It was based on DirectX 9. They're currently undergoing a revision of that, as far as I know, to DirectX 10. I don't know when it's coming out. I just know there's some people working on it. We have VirtualBox, who did an open source graphics adapter, but based it on OpenGL. Insane. But basically, OpenGL is very big. And basing your whole hardware abstraction layer on a huge API is A, insane, and B, security implications abound. It's really hard to prove that you're going to be able to shut this thing, and they're having a lot of trouble. VirtualBox have been going, how are we going to make it even stable? So it's like, they can't upstream their drivers because they don't know what to do. So I looked at that and went, that's a bit insane. They have a bit more, they've got a Windows driver at least started, but they also hacked a lot of things. There was also a project called vGallium, which they actually used the Gallium hardware interface that I was using, but they didn't go to the next level. They basically, it was a research project for Zen. He just basically took the Gallium code in the top and then shoved it out the bottom. So the host had to be running a Gallium driver with a special API attached to it, so it wasn't generic. You couldn't run it on any sort of drivers. It was but it was a research project. It showed that it could be done, but he never had the time or inclination to actually finish it off. But yeah, apart from the VMware one, I think the others have been pretty bad. And yeah, as I said at once, they all shared one big implementation problem, was that I didn't implement them. So, so this is just to give a quick overview of what's involved in the project. Just the pieces, just so you know where I'm talking about things, where they go. So yeah, basically the top 3 boxes are in the guest. There's the kernel, Xorg, and Mesa. There's a KMS driver in the kernel. There's a DDX in Xorg, and there's Mesa Gallium driver. That's the same as a real hardware device. It's no different, as you'd expect. And then on the QEMU side, I have some code that's the basic virtio-gpu that lives in QEMU. And then I have this large renderer library that lives outside of QEMU and is built as part of Mesa at the moment. And then that sits on top of OpenGL, and that does all the rendering. The reason the different colors, the lighter blue color with the really bad contrast is these are the pieces that are required for a simple GPU. So I want to make a virtio-gpu that's sort of extensible. So the basic one is all you need to do is the simple code in the QEMU driver, and a KMS driver. And then you won't have any acceleration on top of that, but it will be enough that it will work when you don't have the 3D bits in place. So it'll work on, also should work on ARM and all of those other things quite easily. And then when you actually want to get 3D acceleration, you need to start plugging in the other bits, the renderer, the DDX, and the Gallium driver. So that's just a quick overview of where the pieces on the stack lie. So I'll start quickly with the basic virtio-gpu. So this wasn't my original plan, but it's sort of where it ended up happening was I originally just wrote all the 3D code first, because that seemed like the interesting thing to do, and then I went, oh, now I got to actually figure out how to upstream this and do it. And the guys are like, well, could you do a virtio-gpu that doesn't have any of that stuff, but is a virtio-gpu that's useful? Still, I can just do, so I basically went, yeah, that doesn't seem too bad. So I basically decided to do a basic virtio-gpu that just does multi-head and gives you hardware cursors. It has no acceleration abilities at all. So I think this was the second project I did once I restarted. It basically, it's a virtio, I don't know if people are familiar, a bit of virtio from Rusty's talk, hopefully. You've got a number of virtual queues to represent your device. For the basic virtio, I've so far spec'd 3 queues. I have a control queue, a cursor queue, and an event queue. So control and cursor are from guest to host, and the event queue is an interruptible thing that the host can use to send something to the guest. It can provide MMIO, PCI, or VGA devices. That's the theory. It should be able to work on anything that QEMU can work on, or anything that virtio works on. Yeah, it should work on all the arches, and it's got a basic 2D command set that I'll quickly describe now to give you sort of an idea of what it's sort of going to look like. So, yeah, so this is the command ring. This is the stuff that gets sent in the first of the queues. So the basic first command is called get display info. It basically is for getting back what's connected. So for multi-head, it basically tells you there's, this size of this screen, the size of that screen, unless you plug in and plug out different monitors and stuff. There's a get capabilities, which is basically, oh, I want to get, what have you got? What can you support? So it's like features, but it's at a higher level because the features are too low level at that point. But then I have some nice little diagrams of other bits. So we've got an idea of resource objects. Resource objects are created by the guest, so it has identifiers. The guest allocates the identifiers and then asks the host to create a resource object with the following parameters. So in this case, create resource takes a width, a height, and a bits per pixel. And that creates a resource inside of the guest. That is not a linear, it's just like, it'll be a GL texture in one case, or it'll be a Pixman texture if you don't have GL. So it's just a storage for.
You said it creates resources inside the guest.
No, sorry, in the host. Yes, in the host, sorry. And then onRef resource just removes it. That's just like a create and remove. So these are the basic building block of the whole thing, is having resources that you build on. The next command then is setting up the scan out. So this means I want to display something in a resource. This is how you tell which rectangle of your resource is to put on the screen. So in this case, I've just made a subrect of the resource.
Can the guest own the host?
Possibly. Depends if, can the guest out of memory the host? Yeah, but no more than, yeah, you're allocating Pixman. If
the guest can create allocations in a host.
Yes.
So you might need some way to bound that.
Yes. But if OpenGL, you're pretty much totally screwed. Yeah, C groups, no. But yeah, so we've got this scan out block. It's got an X and a Y, so an X and Y offset into the resource, and a width and a height of the resource to scan out. So it's just a box. That means, so in a normal case, it won't be a box like that. It'll be a box either the full size of the resource, or if you've got multiple heads on a single resource, it'll be a left and a right, or your standard sort of X window layout of screens. So you'll call set scan out the number of times for the number of outputs you currently have. So I have hard-coded 4 outputs, but there's no reason that 4 needs to be a limit. Then the next bit about the resources, I have this attached backing. This is where it gets a bit complexity. The way it works, the way Virtio works, you do DMA transfers by having a ring with a set of descriptors which you can link to, but there's a limit on how big that number of descriptors can represent. And due to a number of small other problems, I discovered that if you've got a 1280 by 1024 screen and at 32 bits per pixel, it's about 5 megs. And if you use the current memory allocator in the kernel for TTM, which does something really dumb and gives you back pages in the wrong way, you'll get the worst possible allocation of scatter-gather for a 5 meg page, which is one 4096, single 4096s. That overflowed the descriptor table straight away. I was like, okay, that's probably going to happen in real life eventually. Probably once I fix that bug, I could get away, but eventually I'm going to hit this limit. So talked to people, discussed, went, oh, what does real hardware do? Oh, well, real hardware uses a GART. So, well, I'll just do something like that. So I basically created this attach backing API, and you hand the attach backing API a whole load of address and length, like pretty much nearly the same descriptors, and it then attaches those pages onto the object. It doesn't actually do any attach, it just associates that this resource has all these pages in the guest. There's also the opposite of invalidate backing, which will just remove that backing store from that linkage between the resource on the host and the pages on the guest. But it doesn't mean that the pages in the guest are in the resources on the host. They are still a separate piece of memory. The resource on the host is in Pixman or in OpenGL. You can't get those things and stick them in the guest, and the pages in the guest you can't get and stick into there. So we have to have some way to actually put stuff in and out. So there's another command on the command queue called transfer to host, and that takes an offset into the resource and a width, height, x, and y, and it takes it takes an offset into the backing store, and it copies from that offset the box into the resource at that offset. And that's how you pretty much draw stuff. That's like you render stuff in the guest, and then you call the transfer to send it to the host resource, and then finally you flush the resource. So flushing the resource only matters if you're scanning out of it, but you don't want to be in a situation where you're doing 50 or 60 little updates to your front buffer, and then you're scanning it out after each one. You want to be able to do all 60 updates and then go flush this to the scan out. So for things like page flipping and stuff like that. So it's just you want to flush. You don't need to flush anything except scan out resources. Everything else, when you transfer, it's in there. So that's the basic virtio-gpu multi-head, the non-3D accelerated one. That's all you really need to do it. You just need a way to, you don't even need transfer back because there's nothing happening on the host. There's no rendering, there's nothing. So it's all just send stuff. The way other people had done this before was using, I don't use any linear PCI space here. I don't have a bar for this. It's all just guest pages being transferred. So there's no direct access from the guest to resources on the host. It has to use transfers to put stuff in. So it's like an old video card. People probably don't know that this existed, but there was video cards at one time that the VRAM was totally inaccessible, and the only way to do anything was to do DMA transfers in and out of the VRAM. So it's pretty much the same sort of design as those. And it's pretty much what VMware have done. Funny. So I have a cursor ring. This is a second ring. Just I decided all cursor updates happen quite often. Probably should put them in their own ring. It sends an X and a Y, hotspot info, a resource ID that contains the image you want on the cursor, and a generational ID because I screwed up the original implementation. But no, basically, I was sort of going, oh, if the resource ID changes, change the picture, but I was actually using transfers into the same resource constantly. So when you transfer into the cursor resource, you up the generation ID so that it actually knows I need to get the new cursor. So the cursor ring is there. I have an event ring. This is the ring that goes from the host back into the guest. The only thing being sent on this is a hot plug event at the moment. So when your viewer or whatever you're using to do viewing, currently you have a special key combo that just for testing, and that will send an event into the guest saying, oh, a monitor appeared. And then the guest will do what it normally does with real hardware and do all the processing and read the latest stuff. And so it's only a very simple thing at the moment, but I think I may have error events. Maybe the only other thing I can think of using it for. Resize maybe? No, well, resize is part of hot plug. So it's the same. You get a hot plug event for, so that was whether we get resize events. But yeah, resize is considered a hot plug. It's like a new monitor appeared that's a different size. So that was the simple GPU. That's how all you need to do to get a basic Virtio GPU that everyone can use. And it's quite small. It's not a lot of code. Probably should. I don't think there's really anything that would stop us merging it fairly soon. So I have a bit more to talk about when I get to QEMU integration. But yeah, it was pretty simple. The 3D acceleration is a little bit more complex. just a little bit. But yeah, it's got probably I think only actually two additional things over that basic GPU in terms of that low level of stuff. So the command ring, using the exact same command ring, but with just more commands, you can then manipulate certain 3D objects. So contexts, again, this is, if you don't really know how 3D rendering works, I don't want to do a tutorial on that because that would take a day, not 40 minutes. But yeah, you can basically create and destroy a context from the guest in the host. And that pretty much ends up being a GL context that it creates and destroys in the host. And it has all of the information attached to it. For security reasons, oops, I've lost my mic. For security reasons, when you create a resource in a certain, you want to be able to attach it to a context. You don't want everyone to be able to see everyone's resources. We call that gem, and that's our current kernel interface works, but you don't really want that. It's not secure, as we discovered. So there's an API basically that says, attach this resource to this context so it can access it. So the kernel decides which resources get attached to which context, and user space can't do anything bad. There's an extended version of the resource creation command, which takes all of the information you need to do a 3D resource, which is, let's see if I can remember it. It's like width, height, depth. Now that means 3D depth, not bits per pixel. It has bits per pixel. It has number of bitmap levels. It has number of array levels. It has, it keeps going. There's a lot of parameters to create a 3D resource. I think it's got number of samples for multi-sample resources. So it's a quite complex thing, and that's based on the Gallium resource creation command, so it's pretty much the same thing. We have transfer to and from host commands, but 3D variants of those, again, so you can transfer into a bitmap level or into an array level, or you can transfer into things like that. And you've got to transfer from host, because once you start rendering in the host side, you need to be able to read back for get images and read pixels and things like that. So there's a from host transfer as well. And then finally, there's the magic submit 3D command stream. So this is basically, it takes just another buffer, an indirect buffer full of command stream state that user space has created that in the Mesa driver, and it sends that into the hardware. And that's actually where all the magic lives. The basic resource, kernel driver and the virtio interface is pretty much just creating context and creating resources and moving data around. They don't do much more, but the magic lies in that. So I'll get to that. I had to add one more ring. There's a concept in 3D graphics called fencing. I'm not sure where the name came from, but yeah, basically it's a monotonically increasing 32 or 64-bit value that when you submit a command stream or when you submit a DMA operation, you tell the hardware to emit this fence afterwards. So you build up the queue of commands, and in the queue of the commands, you put these fences. And that lets the guest know, oh, it's finished doing that command, so I can then reuse the buffer that command was talking to. So if you've got resources that you're rendering into and you want to read back from them, you have to wait on the fence value that was put after the rendering command. It's a simple concept. So I originally did this using the config space, but was informed that that would be a bad idea for virtio devices. I think the S390 guys went, yeah, we don't do that very well. And then somebody else went, that's a trap. And I was like, okay, I'll use a ring. It's simpler, even though it's a dumb ring. And I think what I'm doing in the ring at the moment is I'm just putting the same page in 64 times. And because I don't care, the number just gets bigger. As long as it's getting bigger, I don't really care. So they're the two additional concepts that happen, except here's the magic. And I've only got one slide on the magic. That's it. But yeah, I'll give you the objects. So 3D command stream, it's built up of the Gallium state objects. And the Gallium state objects are kind of based on the DirectX 10 state objects. State objects in 3D rendering are things like, if you rasterize your state, depth, stencil, alpha state, so things about your depth buffer, depth testing, the shaders, samplers, queries, frame buffer setup, scissoring, viewports, buffer objects. And rendering, so you've got to just draw, set up all the state, do a draw, do a clear, do a blit. You've got queries like what occlusion queries, and yeah, so basically everything that OpenGL and Direct3D need. This is pretty much done with the command stream. The command stream is generated nearly directly from the Gallium interface. So I literally just take Gallium thing and linearize it and stick it into the command stream. And that seems to mostly work. Yeah, so the Mesa, that lives in the Mesa driver, and there's a small bit in the X driver, but it's nearly all in the Mesa driver, and it's not a huge amount of code. Then we have so that was all in the guest. Now we're back out in the host. This is the big library that was sitting over to the side. Oh, excuse me. So the 3D renderer, sorry. This is basically a Gallium state to OpenGL state converter. So inside the guest, you did OpenGL to Gallium using the standard Mesa code. This tries to go the other way. This is not the simplest thing in the world. It's a lot of the simpler GL state is fine. You get state because when you convert it from GL to Gallium, it goes into one of those state objects. It's a bit. You take the bit, you stick it back into GL with the same interface. Some interfaces, there is no way to get all of the things always back in. So there's a bit of some messy complexities around the edges. This is quite a bit of code, but we have a pretty good test harness for running stuff. And once you start doing the numbers are getting bigger, and you go OCD on it, and you just keep going till the numbers keep getting bigger, and you're happy as long as they keep getting bigger. You could spend weeks doing it. I did. It was good fun. The other big complex code in this is, so I didn't say this here, but so who's familiar with like GLSL shader language? So GLSL shader language is like a C-like language. It's pretty high level. In Gallium, in Mesa, we convert that GLSL state into a thing called TGSI, which is, I can't remember what it's now. It used to be the tungsten graphics shader implementation or something, but it's just meaningless now because tungsten graphics doesn't exist. But so it's more like an assembler language than a high-level C language. So it's more basic, and it's pretty simple. It's more opcode based, and you don't have like high-level structures and things. You have to convert that back to GLSL. That's not, so you're basically writing an assembler to C project. It's, messy. It started off okay. It quickly, rapidly went downhill, and I know it's going to get worse. The only saving grace I have is Wine does nearly the exact same thing, because Wine has a HLSL to GLSL converter for converting the Windows DirectX bytecode into GLSL shaders. So Wine have solved some of the problems I would have hit. They haven't solved all of them, but I'm getting there. It's happening.
Scotch will fix the rest of the problems.
Pardon?
Maybe Scotch will fix.
Scotch will definitely fix. Buy Scotch. Give it to me. But you've got. Also, I'm using currently, it produces, the other problem with GLSL is there's lots of versions. There's like, so you have to pretty much target a version. I'm currently targeting GLSL 1.30 with one extension I need, which is the bit encoding extension from some other later version of GL. I thought I could use GLSL 1.2, but I don't think I can make it. It's a bit tricky. But the conversion process is kind of messy. Someone who actually knows how to write things like that could look at it and go, whoa, what were you thinking? Because it's a lot of sprintf or snprintf generating these huge lines, and it's like, it works, but it's not pretty. Thankfully, we don't have to do this all the time. It's not.
I'm not the biggest understanding of graphics, so I might be missing something, but is this essentially the trade-off to not passing the whole OpenGL API down like the other implementation?
Yes, this is the trade-off. You have to do this conversion of state and conversion of shaders.
Can you create bypasses? If you know behind you have a GL,
No.
An extension, bypass the shader straight.
No, Ben wants to know if you could use GLSL to bypass. The problem is the GLSL shader is not just dependent on itself. There's other state objects, values that matter to it, and they're translated at various points. You don't have access at the layer that I'm at, and I don't see the value in it, to be honest. It makes it a lot more complex. It sounds easy, then you go to doing, yeah, if it was just a shader, it'd be fine, but otherwise you're going to pass through most of the GL state.
So similarly in terms of bypass, if your host driver is itself based in Gallium, can you have an API to inject more?
I'm not willing to do that, but it could be possible. So Ben's second question was, on the first one was on the guest side, could you pass the GLSL straight through to the host? I don't like that idea. It's too messy. You need a lot of GL state. The second one was whether you could bypass the Gallium. If you knew you had a host driver that was Gallium based, could you directly write into that instead of using GL? That's what vGallium did. And well, I've got two reasons for not doing it. One is I have customers, no, non-customers, but I have reasons that NVIDIA binary driver should work with this, or other. Yeah, and the Intel driver, for example, doesn't use it. But the other problem is, yeah, it's a lot of code, and you'd have to validate a lot more code, and I don't want to validate that much code.
Is it something where we need to add things to Gallium to make it easier?
Is it something we can add things to Gallium to make it easier? Probably not. Gallium's fairly complete for what it needs to do. So it's more, you could probably add things to GL that would make it easier. So you could feed different things in without having to do so much conversion. Someone had looked at doing a Mesa assembler extension once for Wine that they could use for something similar. So that sort of thing would make it a bit easier. But really, I don't want to put too much requirements on this thing requiring these things, because VMware already works on these drivers and other things already work. So I'd like to at least be able to get this out there working on a good base first and then work my way up. Just a quick aside, what GL versions? Currently, it exposes GL 2.1 and GLL 1.20 in the guest. I actually have it running here with as GL 3.0. I think I have nearly all the features for GL 3.0 exposure from the inside the guest working. There's a few small problems with things like, I don't know if people know, again, it's one of these 3D transform feedback's a bit of a problem because the GL interfaces are really ugly for it. But I think I've got that working. And the GLSL 1.30, one of the problems converting assembler to C became apparent pretty quickly was the Gallium shader language uses untyped registers. So there's no integer or no float or nothing attached. It's the instruction that's operating on the register that tells you how to interpret it. GLSL uses types. So you end up having to do a lot of bit casting API, wrapping around every axis. So you sort of go, okay, I'm going to assume everything's in a unsigned int, and I'll cast it to floats if I need it. So it's ugly, but it works mostly. I think I've only got about 4 or 5 tests left to fix with that. Multi-sample anti-aliasing is a bit tricky as well, but I think I've got most of that working. Again, for that, the host driver needs to be a lot newer than what I'm going to be able to expose in the guest to get it working, because there's certain GL functionality I need that's later. But that's on my list for things I want to get working. Going past GL3 is kind of tricky. GL after 3.0 deprecated a whole lot of functionality. It made a compatibility layer. Kind of got a bit, like, it's a good idea, except the compatibility layer is not exposed on the current Linux drivers. And I don't know how to implement. I'd have to implement some of the older things so if I had a host that was GL 3.2 and I wanted the guest to be able to expose GL 3.2 and previous versions, I would have to somehow render the GL 2.0 commands that were deprecated on top of the GL 3.1 in the host. So it's a bit tricky. I'm going to think, I'm sure there's ways around it, but it's a tricky problem. But there's some other projects that actually do similar type of things. I think someone's got a GL on top of GLES type project. There's a whole lot of these little things in GitHub that sort of do something. So I'll probably start looking into ripping one of those off. QEMU integration. So of course this project is part of QEMU in one place, and that was the one project I've never looked at before. That was my how to run into the problems. So the first problem I had with QEMU was SDL. It's only got SDL1 support. I wanted to do multi-head, but SDL1 can't do multi-window. I wanted to do hardware cursor support, but SDL1 can't do ARGB cursors. So I was like, oh, time to port QEMU to SDL2. So that was like, there goes a month. That was fun. So I pretty much started porting it to SDL2. added the multi-head stuff. That's actually the only code that has been looked at. And I think it's not in yet, but it's in someone else's tree to go in. So it's like, at least I don't have to care about it too much anymore, thankfully. It also raised a number of input problems in the QEMU stack, and these are actually quite tricky to figure out, because if you've got a single QEMU window in SDL, or even in anything, the mouse input is done as if it's a touchscreen. So it operates like a tablet. So when you click on that window, it operates like an absolute touchscreen. Now, when you've got two windows side by side, you then have two touchscreens, because if you try to treat it as one big touchscreen, you don't actually have the information to know, is it left and right, or if it's up or down, or if there's, so you actually can't tell. But if you have two touchscreens, the operating system then needs to assign one touchscreen to each screen. It needs to know that that touchscreen's on that screen, that touchscreen on that. So it gets a bit more complicated. We probably need some sort of agent in the guest to deal with it, and it's a bit hairier. Spice has something already that does this, kind of, but yeah, there's a bit of work to be done in that area. Another thing, I did an initial implementation of this. I think I finished it 2 or 3 months ago, and this was the 3D rendering bit only, and it was hacked. And the QEMU code had like a thread. I just bolted a thread on and just put locking around a few places I thought were right, and then just made this magic thing, and it worked, but it was wrong, very wrong. It was like, it was not using, the thread was looking up memory in the main QEMU process without locking, and yeah, but it was enough to get a speed idea, because when I did the first implementation without that, and the speed was a bit brutal, and then I added that, and the speed went well up, and I was like, oh, wow, that gets really fast. I should figure out how to do that properly. Doing it properly involves this thing that VirtualBox just did, which is called data plane, where they've put a thread for each block device, I think, or a thread, and then you can get MSI interrupts, and you can do process rings. That's pretty much all you can do. So I want to try and use the data plane code for this, because I know it will make a big boost, but when I actually went to go, so how would I do this? It was like, yeah, no, yeah, we need to fix the data plane code a lot more, and there's a lot more work we need to clean up before you could do that. So yeah, so I was kind of like, okay, well, I'm kind of annoyed, but I'm willing to merge this without that work, but I don't want to look at the Phoronix benchmarks I get, because I know they're going to be slow. And it's annoying that they are slow, but I've actually, I did some benchmarks, and I'm still not 100% sure of this, but at one stage, I'm nearly sure I had OpenArena running faster than VMware on the same hardware. So I need to go back and actually make sure of that, but I think I had 350 frames a second, and they had 325, and native was like 500 or something like that. But it was, the numbers were like, oh, I could actually make this as fast, if not faster, than VMware, who've done it with 10 people, whereas I got 50% of my time. So that's fun. Another problem came up. It's sort of in buffer sharing, but it's more about how we deploy QEMU. Right, this is how most distros currently deploy QEMU. You've got a sandbox where libvirt starts up the QEMU process, and it's hidden away, and maybe it's SE Linux away in its own corner. It's not connected to the user session directly, so your X server isn't in charge. If you virt start something, it doesn't connect to your X server. So if you log out, it's still running. You connect via this remote viewer, virt viewer, or something like that. And that's pretty much the standard way it's being deployed now. Right? There's also gnome boxes, but gnome boxes that are pretty similar. It's maybe a little connected to user session, but it's very similar. This isn't what VMware do with their workstation client. Their workstation client, as far as I know, when you kill the X session, it just takes the whole VM out. They've got their server stuff and things, but if you're actually running their player thing on their desktop, it may suspend the VM and then just trash it. But I was trying to figure out how the hell I could keep this, because the sandboxing is nice, it's secure, in large quotes. But how do you access the graphics card? And here's the problem. The only way currently in deployed Linux for you to use a graphics card is using GLX. And the only way to use OpenGL and GLX. The only way to use GLX is to be inside the X session. And when the X server dies or you log out, you're going to lose your GLX connection. So far I've been developing everything using SDL and the GTK front ends for QEMU because they're handy for doing this. But you kill the session, they die, or you can't disconnect an operation. So it sort of left this question: how do I do this? And EGL, which is the embedded GL, sort of being able to run on the GPU directly. A few other projects sort of got into the places where they were useful. So we had a Summer of Code project do render node support for the device, the DRM. So this created a new device node that only one person could access, and they could only use buffer passing to give it the file descriptor to someone else, and it's secure and it's really cool. And that's good for things like GPU as well. So I was like, well, I could use that for this. I could have QEMU running EGL in its own sandbox without connecting to my X server in there. Can't do it on NVIDIA binary drivers, but I'll have to figure out what I'm going to do there. But I then need to get that buffer to the screen. I need a viewer that can look at it. And EGL came to I wrote a blog post on this if anyone was interested in the really bad details, but EGL was like, people seem to create these EGL APIs but forget to create the opposite one. So you've got like, you want to be able to take a texture from the QEMU process, make it into an EGL image, have the EGL image go into a file descriptor, hand the file descriptor over a Unix socket to the viewer. The viewer will then take the file descriptor, put it back into an EGL image, put the EGL image into a texture, and then draw the texture on the screen.
Can't you just move all the rendering to VirtViewer?
No, because
Pass through commands.
it's too slow.
What happens if the viewer disappears?
Yeah.
You just don't execute the command?
That's what happens already.
Yeah, but no, moving rendering into the viewer is too slow, and it also doesn't work when you're not connected to it. And you want to be able to have the disconnected machine actually doing something when you're not actually looking at it. So but yeah, the problem with that pipeline of things was, I think 2 of the stages were missing. It's like you could go to get from the image to the file descriptor, you actually had to go through another stage because the direct one wasn't there, and on the other side, getting from the image to the texture wasn't there with desktop GL, but was there with the GL embedded subset that's on other things. So it's like, but I've only literally done that work a couple of weeks ago to actually prove I could even build the pipeline. So I'm kind of happy I will try and actually use it and deploy it in the next while. So where's the future for this? I would like to get the basic virtio-gpu upstream. I would like to then get the renderer into Mesa somehow, and at least get the basic GL 3D adapter working with SDL and with GTK front ends. Then work on the EGL libvirt problem, the buffer sharing, trying to get that upstream. Then it would be more into like trying to get GL features, trying to get up the GL level inside the guest to approximating what's inside the host, GL4, things like that. Windows drivers are an open. It should be perfectly possible to build a DirectX driver on top of this hardware level because that's what VMware do with their Gallium interface already. So that's just another project. That's something I don't think I will be doing because my boss was like, ooh, tainted, don't want you looking at that. So demos and questions. So ask your questions and I'll hook the demo up because I have the demo on this laptop just because, Apple. So any questions?
So how fast does TouchWaste go?
Pretty good. I've only got OpenArena to demo, unfortunately. Right. Oh.
Mapping buffers, because GL will eventually want you to map buffers, like vertex buffers, into the guest's memory. Are you doing that, emulating that?
No. All I do now is the DMA transfers back into the backing store. So you try to keep the backing store synced with what's in the host.
I think there are some persistent mapping extensions.
Yeah, persistent mapping would work fine as well, though, because you don't ever destroy the backing store. The reason the backing store is actually there is for suspend, resume, and actually hibernate to work, because otherwise when you hibernate, you'd have to read back everything and allocate a whole lot of memory, and apparently hibernate doesn't like that. So
I was thinking, if you're going to toward GPU kind of stuff, you're gonna have a similar problem where you don't want those copies back and forth all the time.
If you extend this to GPU stuff, you've got two problems. Not my problem. You've got them. This is. Oh, I should have said this is not about compute. That's a whole different problem. I thought that I could probably do OpenCL 1 on top of ARB compute shader, but yeah, doing OpenCL 2 with the memory migration, no, not mine. Right, this is, as you can see, I've got an X stipple. This is OpenArena running, hopefully, in a window with Eric's. Like it's not slow. And that's only running now, that's only about 100 frames a second. I've seen it go at 300 or 100 and something. It also doesn't help, because I'm running GNOME shell here, and there's another copy. There's overheads you just don't have when you're running full screen. Oh, sorry, I have to kill the X server before I do that. Yep, I'd probably have to kill everything before I do that. Any other questions while I'm rapidly rebooting?
Do you support any of the basic VGA text stuff for the BIOS?
Yeah, it will boot the BIOS. Ben's question was whether I support the VGA BIOS stuff. Yeah, when you run it in VGA mode, you get a 16 meg bar that's just used for that. We don't touch it once the device driver loads. Yeah.
How do you feel about this versus PCI pass-through?
There's actually, well, I suppose I should have probably said, there's 3 different ways to do this problem. To get graphics in your guest. There's basic PCI pass-through, so there's it booting normally. There's basic PCI pass-through. That's fine if you can afford to dedicate your whole graphics card to the purpose of running something, but on a laptop, for instance, probably not going to do that. You also have to have an output. You can't just put it on the screen on your laptop. You still have to move stuff around. So the second one is you can do what a number of the hardware vendors are implementing. So the NVIDIA Grid solution, which is they basically have a PCI device with something that approximates SRIOV type behavior, where they sub-allocate chunks of the hardware and give it to the guests and then run a binary driver inside the guests, the same driver. And that's pretty much what NVIDIA have been doing for their Grid project, which is the big, huge card doing VDI. So this is, in theory, GNOME shell running. My mouse is working. Oh, no? It's just slow. The other problem is my monitor is really high res here, and I have to squeeze everything into the corner. Yeah, I think I've actually lost the top of my screen because I've had to stick it into the top corner. But this is GNOME shell running inside the guest. It's not brutally slow, it's quite fast, it works quite well. But it seems to be not working as well as it should. but because I've resized the window, it gets really angry. So. But yeah, I can show you it on the real screen if someone wants, but it's, too small up there. I tried to demo multi-head at KVM forum a few months ago and went, can't really put 2 outputs on the screen and use them or show them in any useful way. So people had to just look at my laptop. Okay, any more questions or I'm finished? Okay, thanks.